So let's start our second lecture of the day. So it's a great pleasure for us to have here Dr. Hervé Cottin. Dr. Hervé Cottin got his PhD in 1999 at Paris 12 University. He was postdoc at NASA Goddard Space Flight Center in 2001 and became an assistant professor of chemistry and astrochemistry from 2002 until 2010 at Paris 12 University. He's now professor of chemistry and astrochemistry and researcher at LISA, Laboratoire Interuniversitaire des Systèmes Atmosphériques at Université Paris-Est, Créteil. He's president of the Société Française d'Exobiologie and vice president of the IAU Astrobiology Commission F3. He's an expert on chemical kinetics, experimental photochemistry, analytical chemistry, planetology, astrobiology, organic chemistry in the solar system, especially on comets. He is the PI of several experiments at International Space Station. He was part of the science team of the Rosetta mission and co-I of the MoMA-GC, instrument on board the future European ExoMars rover mission. So, thanks again for accepting our invitation, and please, take the floor.
Thank you very much, Marcelo. It's a great pleasure for me to be here and give this series of 4 lectures. So I will just give you first a brief overview of this series. So I will talk to you about astrochemistry and astrobiology and the links between the two of them. And I've been working a lot on the small bodies of the solar system, so comets, meteorites, asteroids. So this morning I will give you an overview of the Rosetta European mission. I will give you a brief review, a brief idea about the challenges of this mission. We won't get too much into the science. This will be for tomorrow. This morning I will tell you why Europe decided to prepare and accomplish such an ambitious mission. And tomorrow I will get into the details, but not all the results of the mission. Of course, I won't have the time and I don't have the knowledge and experience to discuss all the results, but much the details I will give you will be about the organic composition of the comet and what we learned from this mission. And then on Wednesday I will talk about astrochemistry of the small bodies, a general discussion about that. And on Friday I will give you something that is, well, in between about science and sociology or outreach, something I called Astrobiology Challenge by Astrobiowashing. So it's inspired by greenwashing, you know, the big companies that says, well, we are doing great for the environment, and while they are not actually dealing for the environment. I will tell you about why and how sometimes we hear about some things that people tell, media tell it's connected to astrobiology, but well, if you look into the details, it's not necessarily linked to astrobiology. So that's the overview of the week. You will see that from time to time there will be some animated movies like this one. So it's been produced by ESA during the Rosetta mission. Well, it's very easy to find on the internet. You go on YouTube, you type Rosetta, ESA, comics or animated movie, and you will find them. It's been produced in all the European languages, so you will find Portuguese, and so it's easy to find. So, since I've been informed that some of you are astronomers, some of you are chemists, biologists, geologists, so I will go from a very broad view. So for some of you it's obvious what is a comet, but maybe not for for others. So a comet is what we call a small body of the solar system. It's made of ice. I should say ices, because it's not only water ice. It's also CO2, CO, methane, ammonia, all the kind of volatile compounds that you can imagine that are frozen into a nucleus. And these ices are mixed with dust. And dust are a mixture of metals and minerals. And these small nucleus, that's not something you can see. You have to go to the comet to see the nucleus. When you are on Earth with any ground observatory, what you see is something like that. You see the atmosphere of the comet, what we call the coma. And this atmosphere is then split into two parts, a dust and an ion tail. And the diffusion of the dust around the nucleus make it impossible to see the nucleus, and then you have to go to the nucleus to be able to see it. It's not like an asteroid that you can see from far away. Then for the comet you have to go there. But you can observe from the ground, you can excuse me, you can observe the composition of the coma, and you see that there is dust in the coma, and you can see that there is a large variety of gaseous compounds. It's dominated by water, but there is also a long, long list of other organic compounds and non-organic compounds that are detected in the coma. There are two main reservoirs of comets. I give you a simplistic view because into each reservoir you will have details, connection between the two, but I give you the brief and gross overview of the story. The comets are stored at the edges of the solar system. One of these reservoirs is the Kuiper belt, so it's made of small bodies. It's beyond the orbit of Neptune, and it's in the ecliptic plane. It's beyond 30 AU from the Sun. And then there is what we call the Oort cloud, which is a cloud surrounding the whole solar system, which is made also of small bodies. You cannot say exactly that these are comets when they are in those reservoirs, because to be named a comet, you have to display an activity. And once you're over there, you're frozen, there's no activity. But these are potential comets, because if those objects are submitted to some kind of instabilities, gravitational perturbations, some of them can be expelled from their reservoir and go in the inner solar system. And when they get close to the Sun on an eccentric orbit, they will be warmed, and roughly between let's say between Mars and Jupiter, some of the ices will start to sublimate, and then the coma will build around the nucleus, and the dust particles that are on the nucleus will be expelled and dragged by the gaseous pressure which is expelled from the nucleus. I'm going to talk a lot about a comet called 67P Churyumov-Gerasimenko. So I will say 67P because it's faster. This is not a comet which is going very far away. It must have been far away and originated from the Kuiper belt, but its current orbit is going from 1.2 at its closest from the Sun, so it's further away than the Earth, and it goes up to 5.7 in the outer solar system, so a little bit beyond Jupiter. So it's not going very far, and its orbit is only roughly 6.5 years. So that's a good target for a space mission because, well, you cannot prepare a space mission on a random comet that will show up unexpectedly with 1,000 or more years of orbit. So to go to a comet, you have to select a comet which is well, already known and has an orbit that is potentially available for a spacecraft.
Did this one come from Kuiper belt or the Oort cloud?
Yes, it comes from Kuiper belt. And so it comes from Kuiper belt, and after a few orbits around the Sun, we think that Jupiter gravity disturbed its orbit, and then it contracts its orbit, and then it doesn't go very, very far away. And there are papers and papers about the history of this comet, whether it's a recent comet in the inner solar system or if it's been orbiting already for centuries or more. So, what is a comet made of? One of the first models that has been provided in the scientific age, let's call it like that, has been proposed by Fred Whipple, and he was saying that comets were dusty snowball. So we knew that it was water that was sublimating from the nucleus, mainly water, and it was mixed with dusty particles, so that's why he proposed this idea of a dusty snowball. When you see this picture, this is Fred Whipple, you can have a good idea of what was the representation of the nucleus. So it's something you can see here. Another interesting view of the comets is that since they were formed at the same time than the planets, with the material of the molecular cloud that collapsed to form the sun and the planets, since this material has been stored in cold places far away from the sun, since the comets we observe are relatively small, they didn't experience too much heating, well, people like Mayo Greenberg here propose that they may, not necessarily all the comets, but some of them may have kept a pristine interstellar material within their nucleus. So the building blocks of the comets may have, to some extent, be the interstellar icy grains that were present in our natal molecular cloud. So studying the comets is a way to go in the archives, not only of the solar system, but maybe before the formation of the solar system. So those objects are extremely interesting. So what do they look like? I can go back one step. Here is what we thought they look like. Here is the first picture of the cometary nucleus. So this is a picture taken by the Giotto mission in 1986. You don't see much. And it's been a big disappointment not to have a better view of a cometary nucleus. Why was it such a dark picture? Because, well, if you are expecting something that is mainly made of ice, you are expecting something that is relatively bright with a rather high albedo. And then when you prepare your mission, it was just a flyby. So everything was programmed in advance. So when you prepare, you are getting ready to take a picture, you are planning to take a picture of something which is bright, so you have a small exposure time. And if you take a picture of something which is dark, with a small exposure dark, you see almost nothing. And this is what happened, because actually the big surprise of the Halley exploration was that the cometary nucleus, at least this one, but not only this one, as you will see, the cometary nucleus is extremely, extremely dark. These are among the darkest objects of the solar system. But you see that, yes, there's something getting out from the nucleus. And this is what we knew. Some ice is sublimating. And here you see that there are some jets of gas that are expelled from the nucleus. And this is one of the best pictures of Comet Halley. So this picture was taken 2,000 kilometers by this guy here, Giotto. And you see that he's taking a lot of risk because, of course, the comet Halley was active at the time of the flyby, and yes, no one was here to avoid the dust particles that were, yes, flying roughly at a few kilometers per second. The relative velocity was more than 60 kilometers per second. So even if you take millimeters or centimeters in size of dust particle, you get hit and you get damage. And actually, the antenna of Giotto spacecraft was damaged during the flyby. This is a more recent picture, which is a reprocess of another space mission. This was the Vega 2. This was a Soviet mission who took another picture. It's a recent reinterpretation and reprocess of the nucleus. But you see something interesting. It looks like the nucleus is not round. It looks like two lobes objects. And this is a feature we will find on other cometary nucleus. So there has been a series of other space missions. So interestingly, NASA didn't send any space mission to Halley. Europe sent a space mission, USSR sent 2 space missions, and Japan sent also 2 space missions to explore this comet. But then NASA sent space probes to this comet, Borrelly, in 2001. It didn't do much science. It was just a flyby, but the main idea of Deep Space One was to test some new kind of propulsion for space probes. So it didn't make a lot of science at Comet Borrelly nucleus. But then was the Stardust mission. Stardust mission was meant to bring back samples that have been collected in the atmosphere of this comet, Comet Wild 2. So, well, as I said, the encounter between a spacecraft and a comet is at high velocity. And if you want to collect some material at more than a few kilometers per second, you need to slow it down. And the idea was to collect the dust particle in an aerogel, and so the dust particle would be slowed and captured in the aerogel. So the spacecraft returned successfully dust particle collected in the comet, but for the organic composition, it's been somehow a disappointment. We didn't find much organics in the dust particles, and the velocity of collection was too high, probably to preserve this organic composition, and the people preparing this mission already knew that there was in the aerogel some carbon. And deciphering the carbon from the aerogel, the carbon from the comet, and the chemistry between the carbon of the aerogel and the carbon of the comet at a high velocity impact was a nightmare. It brought a lot of information, but more from the mineral point of view. Temple 1 has been explored by another mission. It was the Deep Impact mission, and the idea was to say, it's a simple but very ambitious idea. Okay, the nucleus of the comet is dark. Here you see pictures that they look gray, but yes, it's dark. The albedo is extremely low. It's low like coal. So don't be abused by these pictures. It's extremely dark. And the idea was to say, okay, the interesting stuff of the comet is not at the surface. It's dark, so let's dig a hole. So one way to dig a hole is to send an impactor and dig a hole and look what is inside the hole. Well, it was successful, but when the impact occurred, so many dust has been lifted then the spacecraft was not able to take a picture of the crater because it took too long for the dust to disperse And since it was a flyby, like all these missions were only flyby, so a flyby is a few minutes of science at the comet, not much. So we've never seen actually the crater, even if after Stardust sent its material back to Earth, the main spacecraft has been rerouted to make a flyby of Temple 1 and try to see a few years after if we could see the crater. But it's still eluding some people think that we see something. But well, wait, when you look at the papers, it's not straightforward. And last Nucleus that has been visited before Rosetta mission was this Nucleus, Hartley 2. It was the deep impact after the impact that has been rerouted to this comet to make some observations. So what are the characteristics you can see? They are dark. You don't see it on the picture, but imagine it's extremely dark. Sometimes you see some surface craters, features. They look like craters, but in the community of people working on the surface of comets, they are arguing whether these are impact craters or somehow, since the ice is sublimating from below, if it's more the surface that is collapsing because there are void spaces that are freed when the ice are sublimating. So it's not obvious. And you can see that for Comet Halley, for Comet Hartley, for Comet Borrelly, yes, it looks like there is two lobes that are joined together. And then the question is whether these are two cometary nucleus that have been connected, softly connected, or if it's an object that has been eroded in the middle. But this feature is rather 1, 2, 3 out of 5 nucleus. Well, it's small statistics, but these are already some statistics. So we go to comets for mainly 2 reasons. They are a reservoir of primitive material. They help us to better understand the conditions that were prevailing when the solar system formed, and also maybe they help us to understand what happened before the solar system formation. And also, when we observe the gaseous molecule from the Earth, since 40 years, 50 years, we know that there are organic molecules that are expelled. We know that it's full of water. So since we know that the Earth formed in the inner solar system at a place where the solid material that made the bulk composition of the original material of the Earth, this material was rather dry. So one idea is to say, okay, we have water, liquid water on the Earth, so maybe this water has been imported at a second stage. And, well, comets are full of water, so why not water coming on the Earth from comets? And with the water, comets would bring a full series of very nice organic compounds. And then we get into astrobiology and prebiotic chemistry. Is there interesting chemistry that can be initiated by the organics that are inside comets? So maybe some of you already saw this kind of graph. This is the D/H ratio in water. Water is H2O, but, well, in some of this water, one hydrogen is replaced by deuterium. And if you do the D/H ratio of this water or the water at the beach or anywhere on Earth, the ratio will be 1.5 10 to the minus 4. So that's the value of water on Earth. don't look at the bottom because here it's measured in hydrogen. So here it's in water. What we see is that in chondrites, carbonaceous chondrites, some family of meteorites, we have a lot of these, we have a lot of statistics, and yes?
How do Mars and Venus fit into this picture, please?
I don't know. Yes, Venus, because we think that Venus, water in Venus has been depleted by escaping. So H2O is escaping faster than DHO. So Venus is enriched. Mars, I don't know.
Mars is also higher, but not as high.
Okay, thank you.
And which this low point to the left? Yeah,
Where?
this one, the left one, in the lower part.
So this
Yes.
is what we think the protosolar nebula.
Oh, okay.
The sun.
Okay.
And these are the
Thank
giant planets, but in H2.
Okay.
So conduits, most of the conduits match, but not all of them. So this is one measurement in Enceladus, which has been made by the Cassini spacecraft. And here are the comets. So, well, comets are rich in water, but the D/H ratio in water is not the same than on Earth. But not for all comets. So this view is the status before the Rosetta mission. And here you see that two comets, Hartley 2 and HMP, well, they fit. Small statistics, some comets are fitting the D/H ratio of the Earth, and some are not. And what you can see here is the origin of these comets. So these comets, which are roughly twice the value of the Earth, are all coming from the Oort cloud. These comets are coming from the Kuiper belt. 67P is coming from the Kuiper belt. So where do you think is the D/H ratio of 67P? I will let you know tomorrow. So some nice pictures of comets. So keep in mind also that comets are somehow fragile objects. This is a picture of a comet taken in 2000, and you see it's called Linear. And you see that over the time, the nucleus, when it was getting closer to the sun, just with the gravity of the sun and maybe the outgassing from the inner nucleus, the nucleus has been destroyed by its own, and the comet disappeared during its orbit in the inner solar system. This is comet Mach-Holtz in 2004. I think that this comet, this picture has been taken in Brazil. I'm extremely jealous because I've never seen such a marvel in the sky. But it's comet Mach-Note in 2007. And well, this is from a view from Europe. I didn't take this picture, but I've seen it, but not that well. And it was in 2020 comet Neowise. So you can see a comet from your own eyes on Earth, but you don't learn much without going there. So, how did ESA decide about Rosetta? Well, one of the first reasons is the frustration of the Comet Halley exploration. Frustration because we didn't see much. And also what we saw and what we understood was extremely promising. We saw that in addition to all the organics that we can observe in the gaseous phase, we saw that in the solid phase, in the dust particles, there were more organics, more complex, more with higher mass, more complex material. So it was a decision between NASA and ESA to bring back a cometary sample, not to do the science in situ, but to bring back the sample. And in 1986, so just after Halley, and until 1992, NASA and ESA studied a Comet Nucleus sample return mission. And then, as often, with project with NASA, in ESA, when ESA decide a mission, the mission has the money until the end. When NASA decides a mission, you have to fight every year, and sometimes you lose. And, well, in 1992, we lose, NASA withdraw, so the sample return mission has been considered impossible with the money that was available in Europe. So the decision was then to send the laboratory to the comet. And that's the idea of the Rosetta mission, which was decided in 1993. The first version was a version with two landers. One lander developed between NASA, JPL, and CNES, the French National Agency, which was called Champollion, and the second lander, which was developed by Germany, DLR. It was called Roland. And in 1994, JPL and NASA withdrew from the mission, and the two lander concept merged into Philae, which was a contribution between Germany, France, and Italy. So it's a long story because the launch was planned in January 2003. So that's not the launch of 2003. The target, which was the aim of the mission, was called Virtanen. It was a rather small nucleus. But Rosetta was meant to be launched on an Ariane 5 rocket, and a failure of a previous launch, one of the first Ariane 5 rocket exploded, so all the program has been delayed, and the Comet is not waiting. So if you delay too much the launch, you have to change your Comet. And you cannot go anywhere. You have a lot of constraints. And the only target that was available was Comet 67P Churyumov-Gerasimenko. But it was a larger nucleus. So you have to figure out that you built a mission for a small nucleus, and then you have to go to a larger nucleus. So more mass, and if you want to land, well, it's an issue. So it's been extremely successful. Launch was in 2004, so it started to be a long time ago. You can see that it's a very long history. Some people were fighting for this mission in 1986. They have to wait 20 years to have this mission launched into space. You have to prepare the instruments during the 90s, and then you have 10 years to wait. Not because we are long and we are going slowly, but because we want not to do a flyby, we want to stay at the comet, to land on the comet, but also to stay at the comet. So the orbit, we will see it in a few minutes, is very sophisticated. It's flight dynamics that is extremely sophisticated. So it's the first spacecraft orbiting, quote, I will show you that it's not really an orbit, it's too small really to consider having an object orbiting around the nucleus. It's more that the spacecraft reached the same orbit than the comet around the sun. It reached the same orbit and at the time where the comet is at the same place. So then you just have to follow the orbit, trust the gravity laws, and you follow the comet with some variations around that. It was the first time we went to a comet beyond 2 AU, because if you want to land on a comet, you want to get close to the comet, and you want to reach the comet when the activity is extremely low. And also you want to see the nucleus So it's harder to see the nucleus when there's a lot of gas and dust that are expelled from the nucleus. And of course, the first time that an attempt of landing was made. So it was extremely ambitious. It was a big, very big spacecraft, roughly 3 meters by 2 and 2. So when you stay next to a full-scale model of the spacecraft, you feel tiny, believe me. It has also 30 meters of solar array, 15 meters each side, because the energy was solar energy. So you need to develop a technology to have huge solar panels that are qualified for space. And there were 11 instruments in the main spacecraft, and Philae was a smaller object, 1 meter in size, and 10 instruments were on board. So it's easy to say, let's bring the lab to the Comet. Well, you have limited size, you have limited capacity, limited energy, and you have hundreds, thousands of scientists saying, it's extremely important to study that, it's extremely important to study that. So people are fighting, developing projects, and there is a hard and tough selection, well, in the middle of the 90s. So you have to see the comet, so cameras in the visible, but in the UV, in the infrared, in the radio wavelength. You have to see it also, but have a close-up. So you have an atomic force microscope to try to see the very tiny grains that are ejected from the nucleus. You have radar, you have mass spectrometers, and here you have the list of all the instruments. So instruments must be small, light, low power consumption. They have to be reliable after the vibration of the launch. They have to be reliable after staying 10 years in space, in the cold. Well, you cannot fix them. You cannot send a team to repair your instrument. Well, if you already work in a laboratory, you know that if you are doing experimentation every other month, you have to fix your instrument or call the service to repair it. That's not possible in a space mission. And you have to be ready for unexpected things, because it's the first time you really do this science at the Comet. And when you do something for the first time in the laboratory, yes, first you take the tool you have, and then you say, no, it's not working. So you go in another lab, you try to find the best instrument, and after a while, you are able to do exactly what you want to do. That's not possible. You need to have something that is universal. That doesn't exist. So the choice of the instruments are extremely important. So I skip this one, but you see all the details if you want to go into further details. And so the imaging goes from meters to nanometers. Philae was meant to land on the nucleus. So it was really, from the beginning, a race against time. So the separation, descent, and landing was programmed on November the 12th in 1914. Then you have an automated first science sequence. So everything was programmed for roughly 2 days. And then you had the long-term sequence. And then the scientists could decide, let's operate this instrument, let's operate this other instrument, for 2 reasons. Because Philae had batteries, so it had a limited time of energy for 2 or 3 days. And then solar panels. And the place where Philae was meant to land was extremely important because it had to get a good insolation to have the energy restored by the solar panels. Otherwise, it was extremely limited. Tomorrow, I will focus on the results based on the organic composition. And so I won't detail all the instruments, but only some of them, the most useful for the organic chemistry. These are the 5 mass spectrometers that have been built, especially for the mission, and that were on the Rosetta spacecraft for Cosima and the 2 Rosina mass spectrometers, and on Philae for Ptolemy and Kozak. So on Philae, we had what we call GCMS, so gas chromatography to make a separation if you have a complex mixture, and then mass spectrometry to fragment the compounds and try to figure out what are the molecules that are inside the mixture. Cosima was built to analyze solid phase. I will get into details about Cosima tomorrow. And Rosina was made of 2 mass spectrometers to analyze the gaseous phase. So we had a very nice suite of instruments to analyze the gaseous, the solid phase, in the atmosphere or at the surface of the comet. So here you have the details about the kind of ionization that was used, the kind of analyzer that was used, the kind of resolution, and the mass range of each instrument. So they were based on various technologies. They didn't have the same capabilities, and they were extremely complementary to allow to analyze a wide range of organic compounds. So the launch. Launch was in 2004. You get from the Earth, you make one second flyby of the Earth. So when you get around the Earth, you get what we call a gravity assistance. So you can change your orbit and you get some additional velocity because it's like you're falling on the Earth, but you try not to fall on the Earth, but you benefit of the gravity of the Earth, and then you get additional gravity. So you see there have been several loops in the inner solar system before going in the outer solar system, and other flybys again before going to the comet. There have been flybys of 2 asteroids during the cruise, and then you see the comet is here. There have been several years of hibernation, and then we reach the comet, and we stay with the comet. So that's why it takes 10 years. We could have reached the nucleus within a few years, but it would only have been a flyby. Now we are with the comet at the nucleus, and well, if nothing happened, we stay here forever. The mission was meant to end in December 2015. Since it was so successful and working extremely well, it's been prolonged for a few months, and it ended in September 2016. So here you can find all the details. So this is the approach. So the first thing you see is that. Well, you don't learn much, but at least you know you're on the right direction. A few days after, you see that. And then you start to worry, because you see that the shape is a bit complicated. Well, for me, I've been working on an instrument on the Rosetta spacecraft, so I didn't have to land. But if you want to land, you have to find a good spot to land. And then you're not very happy about this shape. And then when you see the full picture, it's a nightmare. It's a real nightmare because there's no way to land. I mean, nothing straightforward. It's a very chaotic terrain, very inhomogeneous surface. You have pits, you have cliffs, you have boulders, and you want to land something for the first time here. And you don't have months or years to pick your spot. I don't know if you follow a little bit all the discussion about Mars, and when the scientists and the agencies decide where to land on Mars, they spend years of fights, argumentations, science to decide where to land. Here, you have a few weeks. Because if you wait too much, too long, well, first, the Rosetta spacecraft cannot do everything he wants to do because you still have the lander attached on it. And and the comet activity is increasing. And if you wait too long, well, you won't be able to get close enough from the nucleus to make all the landing operations. This is the kind of boulder you can see at the surface. And you really don't want to have Philae falling here. I found this view graph. So this is not a real picture, but it gives you a good idea about the scale of what you see. This is a huge boulder. And Philae is a 1 meter square that you want to land. So we've learned pretty quickly a lot about the nucleus of the comet, its size. So it's 2 parts, and we didn't know at that time whether it's been 2 parts that have been merged. So it could have been 2 nucleus for the price of 1 mission. You have the volume, the mass, the density, the porosity extremely quickly. So you see that the porosity extremely high. The comet basically is made of nothing. It's made of voids. It's not large gaps or caves. It's a microporosity that is mainly building the nucleus. So these are the kind of views that were made at the time to give you an idea. I've tried to find such a view above Rio, but I've not been able to see it, so I kept Paris. And this is for me, one of the most impressive picture of the mission. This is what we call a selfie, because you see the spacecraft, and the picture has been taken from the spacecraft. Not really the spacecraft. This picture has been taken by Philae when it was still stuck at the spacecraft. And Philae has a series of cameras all around it. And this view, you could see the 15 meters solar panel here. And here, a few kilometers away, 16 kilometers away, you see the nucleus, and you can see a jet of material that is expelled from the nucleus. So this is one of the oldest objects of the solar system, and on the same picture, one of the most recent and one of the most advanced technology that are on the same view. So I have a lot of nice pictures like this. You see this impressive view also of a jet from the nucleus. And when you look at this picture, you could figure out you are on Earth and in mountains, and you see rocks. But it's microgravity, it's mixture of rocks and a lot of organics. There are ices below. It's not what it looks like. Well, and some random terrain where you want to land. So I said we were not exactly orbiting around the comet, and you will see that's correct. This is the complete orbit of the spacecraft, so arriving in August and September. Then the delivery of the lander. And then, well, you have scientists who want to be close to the nucleus, scientists and instruments who want to be far away from the nucleus. You have flight dynamics who say, okay, no, we cannot go too close from the nucleus because it's not safe for the spacecraft, because there are a lot of material that is ejected, and you have to figure out to make everyone happy. Well, I've been involved into some discussions. It's not easy, but in the end, the result is quite impressive. We are beginning 2016. The people working on the ionosphere, for instance, who are interested in plasma, they really wanted to be far away, but I mean hundreds and hundreds of kilometers away. But when you are that far away, you get no material, you get no molecular composition. So you have to find the better deal. And this is the end of the mission. So a few words about the Filet Landing. So finally, people decided to land on this spot. So sorry for the French, but so I have all the information I need. So the idea was to separate Philae. So it was in the morning in France, and it was just pushing Philae. There's no navigation. So you have to get the spacecraft into the right position, and then you push Philae, and it falls. So there's nothing else. So if you miss something, it's lost.
How much is Philae's trajectory affected by gravity?
How much is it affected by gravity? I'd say almost nothing.
It's a toss.
Yes, yes, it's really a toss, and you really want to land where you decided to, where it's not too chaotic, because you really want to land on your feet, and that's another issue. You don't know where you land. You don't know if it's soft, if it's hard. So you have to be prepared for everything. So the idea was to have the feet of Philae that were adapted to something rather soft. If it's like fresh snow, you don't know, it might have been something like that. It's microgravity, so you don't want to bounce. So if it's soft, there's no risk to bounce. But if it's hard, you can bounce. And if you bounce in microgravity, you can reach the escape velocity, and then it's lost. So the idea was to have some anchors that would be fired and attached to the ground. And the idea was also to have some gas release from the top of Philae to kind of comprime to stick Philae on the ground. And during the night, before the Filet landing, people realized that the gas release would not be working. So they have to decide within a few minutes, I think, tens of minutes, whether they cancel the landing or whether they continue. But they decided to continue because they knew it was broken for some reason. It was broken. And to prepare for another landing would have taken probably weeks, if not months, and it would have compromised the remaining of the mission. The radio delay was 30 minutes. No, there's no immediate feedback. Yeah. So this is not a real pictures, but this is what was the view, what was the prospect of the landing. this is what happened. So these pictures were taken from Rosetta spacecraft, and you actually see Philae going further away. So we knew that it was working pretty well because you can see the fits that are deployed. It was turning the way it was meant to turn on itself. This is a picture that was taken from a camera that was below Philae to see the approach of the nucleus at 3 kilometers away from the nucleus. And these pictures, it's a montage that has been made after. All the pictures I've shown you before, it was before landing. And here is the touchdown point. Before, here. After, here. Well, you don't see Philae. While you see Philae here, 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 when it was falling to the surface. And it took a few hours to realize that Philae actually landed, but the firing of the anchors did not work. And then it bounced. But luckily enough, it bounced, but it didn't reach the escape velocity, and it fell back somewhere on the nucleus. Somewhere. Nobody knew where. But we were able to take a picture, like this one. So you are somewhere on the nucleus, somewhere you were not expecting to land. And here you see almost nothing because it's extremely dark. So that's the bad news. You land on an extremely dark environment, and very soon you understand that you won't have enough sun to fill the energy with the solar panels. So it's a race against time, and there has been 2 days of science, measurements, very limited science, but very good science with Philae during this very limited time. And we found Philae at the end of the mission. Almost 2 years after the landing, after several attempts to detect where it was, the OSIRIS high-resolution camera of the spacecraft spot this. I mean, it's not OSIRIS, the people working of the pictures taken by OSIRIS spot this. Right in the edge, a few seconds later, Philae would have been outside of this frame, so we would not have known where it was. So it's here. So the landing is here, and it bounced. We know it bounced several times, and it's been there.
How far is it?
It's roughly less than 2 kilometers, I think, because the size of this lobe is 2 kilometers. Yes, and all the reconstruction, yes, you can confirm it's really Philae. So, as I said, when the comet is getting closer to the sun, the spacecraft has to get further from the nucleus, but it shows some spectacular view, like this one. We called it the summer 2015 fireworks. You have that kind of picture, so these pictures are separated by a few minutes, and you see this, a jet. And when I see that, it reminds me these movies. I don't know if you've seen Deep Impact, but this is, well, they're not on Philae, but it's a good idea about how dangerous it is to be at the surface of a cometary nucleus. But that's a risk. And this is the end of the mission, the trajectory at the end of the mission. So the idea, well, there were two possibilities. We had to stop. We had to stop because we are going away from the sun, and we were reaching distances where the solar energy was not enough to operate the instruments. So at the end, during the summer, we had to pick between different instruments. We could not run science as usual. So one possibility would have been to get into hibernation. oops, sorry, would have been to get into hibernation again and to wait for the comet and Rosetta to return. It was a possibility. But then it means you have to save your resources. You're not sure to be able to awake the spacecraft after 2 or 3 years of hibernation, and you have to save your resources to be able to use your instruments after the comet returned. And the second possibility was to say, okay, let's have our best life, let's do our best science, let's take risk, and it's what we did. You've seen we've been closer and closer and closer from the nucleus, and finally go on the nucleus. So it's not landing because it wasn't meant to land, but it was crashing at the comet surface. So you see the last pictures. I really like this one. And here we are at 6 kilometers from the nucleus. Here, but you don't see because it's in the dark, but we are 1 kilometer from the nucleus. And here, well, it's the last picture. Very disappointing, isn't it? It's blur. But you built an instrument to be extremely good from far. So there are all the reasons to have blurry pictures when you are near, because it's not built for that. But you can do some data treatment to get better results. And this is the end of the mission. Just to so you can understand. So this is here you see the signal of the spacecraft coming from the spacecraft to the Earth. So all the information is here in this peak. And you will see the end.
We just have had a loss of signal at the expected time. This is another outstanding performance from Flight Dynamics. So this is the end of the Rosetta mission. Thank you and goodbye.
How joyful. It was, you know, we used to the beginning of missions. You know, when we land on Mars, when we arrive at a comet, when we fly by Pluto, it's you've seen these pictures of people which are cheering. It's a success. Here, we spent 2 years. People were taking no or very small vacation. We had data all around weeks, all around the years. We were working a lot, and it was working extremely well. And then, yes, suddenly it's the end. And yes, we had very mixed feeling. The joy to have been part of a very nice experience, and also knowing that, well, there will be no similar space mission in the future. So the science will be addressed tomorrow, just because I'm not going to get into too much details about the surface features. I'll go into the composition. Just to let you know that there are a lot of features, of surface features that are interpreted by the fact that this comet, not necessarily all the comet, but at least this comet is a very primordial object. Why? Because you see some structures that are extremely layered. You see that those caps that makes you think that you see the accretion, that inside the cometary nucleus you have some cometesimals that probably formed before and accreted to make the larger nucleus. Here, this we call them the goosebumps, and you see it all around the nucleus, especially when you look into pits and when you look inside the nucleus. The cliffs are made of things like that, and they are all roughly 1 or 2 meters in size. And it's interpreted by the fact that, yes, the comet built from those tiny grains that are created to form centimeter size, meter size, and those meter size are created to grow like this. One last thing, which is important, I think, is that what we see is something that has been transformed because there is dust that is ejected and falling back. But the ice is not at the surface. You can see frost and recondensation of gas, but the ice is below. And it's not much below because each time the comet is circling, orbiting around the sun, it loses a few meters of surface. And the calculation that has been done is that the erosion is limited to the few first meters, and that the thermal inertia of the nucleus does not allow the heating of the sun to go far inside the nucleus. And a few meters below, you have the original composition. You don't see it necessarily from the top, but we have evidences that this comet is extremely pristine and that this pristine material is a few meters away from the surface. Thank you. And tomorrow I will tell you more about the composition. You have to see it into like a two-part lecture, of course, because it would be frustrating to stop right here. Thank you very much for your attention.
Thank you, Hervé, for this great talk. So, questions? Portuguese, in French, in English?
So, Hervé, thank you so much for this amazing story. It was really great. I can't imagine how the team was involved in everything for such a long time, and it was really impressive. Thank you so much. And my question is, how can you tell the difference between the two hypotheses to describe that comet, if they are two nucleus that collided and or if it was a larger body that was eroded by?
So the geologists who reached this conclusion studied the orientation of the layering of the two lobes, and their conclusion is that the orientation of the layering on the two lobes is not the same. It's the same nature, but the orientation is not the same. So if it had been a parent body that has been eroded from the middle, then the layering should be homogeneous all around the body. What they see is that there is a significant difference in the orientation of the layering, which makes them conclude to the fact that it's two bodies that merge. But they merge at very low velocity, and from the composition, well, there are differences of composition in the gas, but it's related whether you're on the north or the south, and the insulation, not really in the gas that is emitted from the big or the small lobes. And what I will show you tomorrow in the composition of the dust, also we don't see two families of composition of the dust which could be related to one nucleus or second nucleus. So the idea is that it's two comets that form probably in the same environment and that merged. So they formed with the same processes. That's interesting. And they merged, and they kept their original composition because, well, if it had been a big impact, we would have lost most of the what we call hypervolatile, so N2, O2, argon, xenon, and they're still there.
Hi, thank you for your talk. How long did the Philae lander operate on the comet, and what measurements were taken in this time, please?
So it lasted 3 days. 3 days, so one instrument did not work, the X-ray instrument. Otherwise, there has been some radar measurements. So this is an extremely interesting experiment because there were 2 antennas for the radar, one on Rosetta and one on Philae. And so they were communicating through the nucleus. So not through the whole nucleus, but one small section of the nucleus. And that gave very interesting details about what I said before, the microporosity of the nucleus. So this worked extremely well. I will talk tomorrow about the composition. The GC, the gas chromatograph, did not work. There has been one run of gas chromatography, but since Philae was, well, it was like that on the cliff, and the sampling system. So since it was like that, it could not reach the surface. So the instrument worked, but it didn't collect any material. But luckily enough, when Philae bounced at the surface, it probably expelled some dust, and some dust entered inside Philae, and it entered during the automatic sequence. So there has been one mass spectrum for each mass spectrum, so Ptolemy and Kozak, and they measured some composition at that time. There have been some pictures too. Well, it's really a pity because everything was functioning except everything that was meant to keep Philae on the ground and prevent it from bouncing.
Yeah, thank you.
Another question?
Hi, thank you. I'd like to know if every data that was collected from this mission, if you already explored everything that you have for science, or if you still are trying to get more results from the data.
It's an excellent question. No, we are not through. Actually, right now I have a PhD student still working on the interpretation of the mass spectra. What you need to think that during the mission, you are really in a rush. You are in a rush because you are doing both operations. So you have to get the data, understand the data, and it's not straightforward, and say what is the next move. So every week we had one or two telecon with the team of the instrument to discuss and interpret. And then you have the pressure to publish because to show that the mission is a success, you need to publish. So you need to do the operation, interpretation, sleep, publish, and after the end of mission, you get all your funding stopped. So you have to fight to keep working. And yes, I will show you tomorrow that there are still papers published and very important results, I think, that are published in 2022. And yes, there are tons of data. We are really on a golden mine. But since, well, maybe you're young, you don't know yet, but sometimes you go where you can have the money to fund your research. And that's a drawback of these missions. So yes, so the data are public. They are archived by ESA. But well, people tend to go to the new mission, to the new results. Most of the colleagues with whom I worked on the data now are working on OSIRIS-REx and Hayabusa 2. so some sample returned to Earth, and we are less and less working on the old data. But I try to keep, because I'm convinced, at least for the composition, we're far from having the old picture.
Thank you.
On this line of what's the next step, but probably in a very longer term, are there any plans, any perspective of landing another mission on another small body?
So small bodies, yes, there have been OSIRIS-REx, Hayabusa 2, but for comets, one mission is decided by ESA is Comet Interceptor. Comet Interceptor is a space mission that will be launched and parked on the Lagrangian point of the orbit of the Earth and wait. Wait for what? Wait for an unexpected comet. Because for those missions, as I explained, we have to go to known objects. We think there's a lot to learn if we go to a comet that gets into the solar system for the first time. So there won't be a lander, it's not a huge mission like Rosetta was. But it will be made, I think there are 3 tiny spacecraft that will get through, it will be just a flyby, the atmosphere of a comet. And what we hope is that it could be an interstellar comet. Because we know now that there are some comets that come from other stars, and that would be, I'd say, the graal of comet exploration, because it tells us so much about our history. If we can get to the history of another star and system, it would be huge. And next, but it's not been selected, even though there are proposals at each opportunity, is the sample return. Because, yes, what we did, well, you have to imagine that we worked with instruments that were built for space in the 90s. And if you know that there is a huge gap between the top instrument in the laboratory and the time it takes to be able to put it into space. So yes, I'm doing mass spectroscopy, but I'm a specialist of mass spectrometer that has been built in the 90s, which was probably the top of the mass spectrometers of the 60s in the laboratory of the Earth. So it's well, you have to deal with that. But sample return, yes, it would be huge, but it's not like Hayabusa or OSIRIS-REx. If you want your sample back, you want it cold. So that's extremely costly. It's not impossible, but you won't get your sample at the surface because there's no ice at the surface. So you have to dig to get some icy sample. Well, it's yes, it's for your generation.
Thank you very much.
Okay, and next question.
Yeah, you showed the disappointment of this last moment when it hit. Was that maneuvered or orchestrated such that you could see the impact from Earth and analyze the composition of what was brought up by that impact and how big a hole was made, or was that just said we're not going to look at it? And also, was the orbit of what was it 67P we're talking about here, or what?
Yes, 67P.
Was its orbit changed at all? For example, a month ago, NASA said, "Oh, I'm going to go into Didymos and Dimorphos, and we're going to measure the change in that orbit." But was 67P's orbit changed at all?
No,
So
not
big.
at all. Because the idea was to go slowly, because we wanted to run analysis as long as we could, because. For instance, there have been measurement pictures. So we wanted a lot of pictures. We wanted to get a lot of mass spectra as close from the surface as possible. So no, it was a soft crush.
So you couldn't see anything from the Earth.
No, because the comet was still.
And you didn't try to measure the slowdown of its rotation or difference in its orbit?
I think it's negligible because it's
So big.
It's so big. It's 4 kilometers, and so you have something which is 3 by 2 by 2 meters. I think the touchdown was a few meters per second. So there's nothing you could. Yeah, no chance you could change the trajectory.
So a quick question.
Wonderful talk. Congratulations. Just about, I'm thinking right about density. Using these radars you mentioned, do they map, for instance, like the external surface and the interface between the solidest part and the other? Is there any model, for instance, is the interior really solid, or it could be like something that you also could stick your hand because gravity is so small?
One of the surprises is that it bounced, and it seems that the surface is rather I don't know, hard. I mean, it bounced in a way that says that yes, it's not. So it's not sand. No, it's maybe some places there are dunes that are made of the dust that is expelled and falling back. But where it landed, it's the immediate surface is. You can see here. You see the feet, the 3 marks of Filet feet here. This is before. This is after. So it's somehow soft, but it's my understanding, because I've heard about that, but I've never even read. It's at some point it got hard, and it's been ejected.
The shape of the interior part is basically the same.
It's like there was some regolith, and after it passed through the regolith, it bounced back in the harder surface that was beneath the regolith. Something like that.
Yes. No,
Asking.
it's not regolith, because the surface is made of the tiny. Sometimes you see that there are some tiny grains, but it's not regolith. It's more dust that is expelled and falling down.
It's finer. Regolith is finer.
Yes, probably regolith is finer. Yes.
So there was this fluffy initial surface, and it must have bounced back into something harder, hiding just beneath this fluffy stuff.
Yeah. But this is the primordial stuff. But you have to keep in mind that it's the temperature is very low too. So, and you have ice, so maybe it's already reached a pack of ice, or it's been compacted, and I can get very far about this subject.
Okay, so let's thank Hervé again.